In this chapter, we will be looking at rational functions and equations. In this lesson, we will be reciprocating linear functions.
Hi everyone. All right, in this chapter we're going to take a look at what we call reciprocal functions, or it might even be better if we had discussed this as the reciprocal transformation. Because really what we're going to do here is we're going to take functions, both linear and quadratic, and we're going to reciprocate them, okay? And we're going to take a look at what that does to the graph. So you've already seen sort of transformations before where we move things left and right, up and down, stretch things, flip things, sort of thing. Well, we're going to do that, a similar sort of thing, but with this reciprocal transformation. Now remember, what a reciprocal is, we take that fraction there, a over b, and it becomes b over a. Just like if you've got any kind of non-zero real number, the reciprocal of that value is simply going to be 1 over, okay, that particular value. That's all we're doing. 1 divided by that value. So now if we've got a function here, we've set up some sort of relationship, functional relationship, y equals f of x. To get its reciprocal function, it's simply going to be y equals 1 over f of x. And that's going to be true so long as f of x does not equal 0. When that happens, there's a natural restriction on the domain here, so because we can't allow that to occur, so we're going to avoid that. Anyway, let's take a look at just a couple quick examples of how this works. All right, so now what we're supposed to do with this particular function here is write its corresponding reciprocal function. Now, that is as straightforward as doing this. We take that entire function and reciprocate it. We simply make it 1 over that negative x plus 2. Now, we should probably add to this that I can do that so long as x does not equal positive 2. As soon as x equals positive 2, the negative makes it negative in front, and then negative 2 plus 2 is 0, and division by 0 is undefined. So we can do this, we can reciprocate it so long as that's not true. Okay, so as long as x does not equal 2. Over here, similar sort of thing. I'm simply going to make it y equals 1 over this 3x minus 5. Okay, basically whatever that function is, I simply write it in the denominator. And again, that's going to be true so long as I don't allow x to equal what? Well, what would make this function equal to 0? And the answer is 5/3. Okay, remember we set 3x minus 5 equal to 0, bring over the 5, divide by 3. So 5/3. And so that's the restriction there. So as long as that's true, that's the reciprocal of that function. Right, so the next point that we want to make, and we are really just taking it slow through this concept so that hopefully this makes sense to everybody. If you've got a point xy on the original function, okay, then when we reciprocate that function, bear in mind that y is f of x. Okay, that f of x is the y coordinate. So when I reciprocated that and I got a brand new y that was 1 over f of x, this is 1 over the old y coordinate. Okay, I recognize that there's an x in there and that the x is dropped into the denominator, but only because it's part of the entire function. Okay? Back in this previous questions, when I reciprocated this, I did not make this negative 1 over x plus 2. It did not become 1 over x plus 2 like that. Okay? I didn't just reciprocate the x, I reciprocated the whole thing. Now, that means that any point that I get, any point x comma y, is going to become the point x comma 1 over y. Because remember, y represents the entire function, the entire value there. So, when we ask for the reciprocal, that's what we're looking for. X stays the same, only the values of y's reciprocate. So let's take a quick look at a problem here. So with these problems right here, all we have to do here is find the reciprocal of each point here. So again, it's the y coordinate that gets reciprocated. So the point 2, 5 becomes the point 2, 1 over 5. Okay? The point negative 3, negative 4 becomes the point negative 3, 1 over negative 4. Now, we would typically not write it like that. It usually looks a little weird to have that negative in the denominator. But because a positive divided by a negative is negative overall, I can move that negative up to the numerator if I want, and that's okay. Here, again, whoops, it's just the 1/4 that gets reciprocated, the y coordinate. But when you reciprocate a quarter, that's going to bring the 4 up into the numerator. You're going to get 4 over 1. Okay, but we already know that 4 divided by 1 is just going to be 4. Here becomes -2. Now, 1 over -1, that's kind of an interesting result there, because when you reciprocate a 1, it becomes 1. It doesn't change. So 1 divided by -1 is still -1. A point like this that doesn't change, we call that invariant. Okay, this particular transformation didn't change anything. Similar sort of thing here, 3 comma, it'll be 1 over 1. But again, 1 over 1 is just 1. Again, that didn't change the point here, so this becomes invariant as well. These points don't change when you do the reciprocal transformation. So any point that's got a y coordinate of -1 or +1, those aren't going to change. They're going to stay the same. Now here, when I do this, I'm going to get 1 over 0, but that should immediately be a red flag here. This can't be done. This is undefined. Okay, we're trying to reciprocate the 0. You can't do that. Okay, so now what we've got here is we can kind of sum this up here. Sorry, I'll zoom out a little bit here. So what we've just pointed out here is that when you reciprocate that function 1 over f of x, you're going to get invariant points, okay, where y is equal to 1 or -1. That's because when you reciprocate those values, they don't change. And additionally, if you get an x-intercept on the original function, okay, now bear in mind the x-intercept is going to occur where the y coordinate is 0. Remember that with a reciprocal function, you are reciprocating the y coordinate. So if the y coordinate is 0, that's immediately going to lead us to a problem. It's going to become undefined there, okay? Now, that means that there's going to be this weird sort of a gap in the graph where all of a sudden there's a spot where the graph is no longer defined. Now, in its place, we're going to draw a dotted line, and it's going to represent this thing that we call an asymptote. We're going to talk about that in just a moment. All right, so now we're talking more about reciprocal functions and their properties that are kind of unique to them. And one of the things that is unique to a reciprocal function is that it's got asymptotes, okay? Now what an asymptote is, and this definition right here, it works okay. It's not perfect though. A line that the graph approaches but never touches. Now see, this is not exactly true. It is possible to touch an asymptote. I think maybe what a better way to describe that is that for large, how do we say this? For large x values or y values for that matter, okay, for large values of x or y, the graph approximates, approximates the asymptote. Okay, now in other words, what I'm saying here is that when you move away from the origin, and really far away from the origin, for large values of x, either horizontally or large values of y vertically, then the graph that you're drawing, once you get way out there, starts to look more like this thing that we're calling an asymptote. Okay, now for vertical asymptotes where the graph is undefined, what happens here is typically you'll get something like, we'll draw something like this, a dotted line, and what you'll see is the graph swoops up against it like this and then swoops down like this. So what happens here is as the x coordinates of all the points on the graph, as those x coordinates get closer and closer to this number right here, whatever that is, your graph gets larger and larger and larger really, really quickly. Okay, there's what we call an asymptote there. So now if you were to kind of like think about this graphing on your phone, if you were to take this and shove it down, and you move up the graph here, your graph that you're drawing would get closer and closer and closer to this vertical line. Now, it would never touch it. Okay? It would never touch that vertical line, because if it did, then that means that there is some sort of a point associated with this x-coordinate. But what we've just established here is that, no, it's going to be undefined there. There is no graph there. The graph is undefined at a vertical asymptote. Okay, so let's say that this is the point 2. We've established that x cannot equal 2 on this graph, and what you get is this vertical asymptote. Also, this gap where the graph gets close to it, but then swoops off to infinity. It never actually touches the line. For a horizontal asymptote, now for most of our horizontal asymptotes you're going to see in this course, it's going to be y equals 0. Now, it doesn't have to be, but it's typically going to look like that. For a horizontal asymptote, you get this horizontal line, and as you move further and further away from the origin, what happens is the graph tends to get closer and closer and closer to it. Okay? Now, generally, and particularly in this course, it will be this way. Generally, your graph can't touch the asymptote. It can't actually cross it or intersect with it. Now, that's not true in general, though. In fact, in general, for the horizontal asymptote, it can behave a bunch of different ways. Let's say here's your asymptote right here. The graph could cut through it, drop down, and then come back up to it. Okay? So it does cross it once. What's important is as you move further along in one direction, as you go in one direction really, really far away, it gets closer and closer and closer to that dotted line. It could also do something like this. Okay? And all of a sudden it crosses it back and forth, back and forth. In fact, it crosses it an infinite number of times. But as you go further away, as the x-coordinates get really, really large, this line here, as it swings back and forth, it stays closer and closer and closer to that line. And so as we go further on, it approximates that line quite closely. Okay. Anyway, that's how we're getting these asymptotes. Now, in general, for reciprocal functions with a degree of 1, so we're taking some sort of linear function, reciprocating it, we're going to get it looking like this, 1 over x minus a, and we're going to get a vertical asymptote at x equals a, because that's where it's undefined. Okay, it's undefined at x equals a. And if you think back, I mean, if it helps to think of it like this, in Math 10, when you were learning about lines, you learned that the slope of a vertical line is undefined. Well, that's essentially what we got going on here. It's undefined at x equals a. We've got this vertical line right through there, x equals a, and that's my asymptote. Right? Anyway, let's take a look at some examples here. All right, so this question asks us to write the equation of the vertical asymptote for each reciprocal function. Okay, so here it's where these things are going to be undefined. And in this case here, when x is equal to -5, okay, that's where the function's undefined. So that's the vertical asymptote. That's that vertical line that this graph approaches. Here, a little bit more complicated. It's going to be where the denominator goes to 0. So it's going to be where 7x minus 2 is equal to 0, where 7x is equal to 2. So x is equal to 2/7. There's my vertical asymptote. Over here, again, where the denominator goes to 0, so bring the 10 over, 5x is equal to 10, divide both sides by 5 to isolate the x, and we get that x is equal to 2. Okay, let's look at another one here. It says use the graph to identify the characteristics that were asked for here. Now, if you take a look at this graph here, now the very first thing I'm being asked for here is the domain. I'm assuming that this graph extends left and right indefinitely here, but notice that it seems to have a problem right near the y-axis, which is where x is equal to 0. So what we're seeing here is that x cannot equal 0. Okay. Now, again, look at the little arrows here. Goes up infinitely, comes down infinitely, but you know what? As it approaches the x-axis, it swoops out here, meaning that there's some problem here with the x-axis. Now, that's where y is equal to 0. So the range must be that the y can't equal 0. Now, the result of this is, the vertical asymptote is that x does equal 0. That's the equation of that line. The horizontal asymptote will be y equals 0. That's the equation of the line that the graph is approaching. They are related to the domain and range. Okay. Now, the vertical asymptote will always be related to the domain. Okay. The horizontal asymptote, like I suggested before here, may or may not. In this particular course, very likely that's what's going to happen. Just be aware that that doesn't always have to be that way. Okay, we're going to do the same thing with this graph right here. Notice in this case, though, again, we've got this little arrow going to the left, arrow going to the right, but there does seem to be a problem here at x equals 1. This is where the graph is shooting up to infinity. So there appears to be a problem at positive 1. So x can't equal positive 1. Now, horizontally, okay, if I go left and right here, okay, the graph goes on forever. But notice how that translates into how the graph behaves vertically. As I go left and right forever, the graph drops down to the x-axis from above. It doesn't actually come from a below. And if you come towards positive 1 here, it shoots up to positive infinity. Now, the graph is never below 0. But based on the way this is drawn here, I'm assuming it never gets to 0 either. So my range is actually going to be, in this case, that y must be greater than 0. Not even or equal to, just greater than 0. So my vertical asymptote here will be x equals, whoops, sorry, not x equals 0, x equals 1. But my horizontal asymptote in this case is going to be y is equal to 1. Sorry, man, I totally got those flipped there in my head here. Y is equal to 0. It's the x-axis that is the asymptote here, okay? The graph drops down as you go further and further away from the origin. As your x-coordinates get larger and larger, the graph itself, its y-coordinates are getting closer and closer and closer to 0, the x-axis. And that's true in both directions there. That's my horizontal asymptote. Y is equal to 0. Okay, so now we just want to take a look at some guidelines when we're graphing reciprocal functions. So you take your y equals f of x and it becomes 1 over f of x. And we want you to be able to sketch these things without too much difficulty. So we're trying to develop this more of an intuitive way of sense of the way this works. So first of all, what we're going to do is you graph the original function, and what you want to do is either on a table of values or on the graph here, just identify the main points. Okay, those could be intercepts, okay, vertices, okay, just points that jump out at you as being significant. We're going to mark the invariant points. That's wherever y is equal to plus or minus 1. Now, usually what that means here on your graph is we would draw this kind of horizontal line at y equals 1 and y equals negative 1, and wherever they intersect with the graph, those become your invariant points. Okay? Now, important, the x-intercepts of the original function become your vertical asymptotes. That's because, remember, the y-coordinate is supposed to be 0, and when you reciprocate that, you get an undefined. So we're going to identify those for sure. Then what happens here is all the values of y for every point on the graph get reciprocated. Now think about the way that works. If you take a large number and put it in the denominator, the result is a small number, a very small number. However, if you've got a really, really small number, and I'm talking in terms of absolute value, not with the plus or minus there, just a very, very small number here, whether it's positive or negative, if you reciprocate it, you're going to get a very large reciprocal, whether it's positive or negative, okay? And that kind of movement here, basically it moves in the opposite direction that the original graph goes. So when the original graph goes down, the reciprocal is going to go up and vice versa. Okay, let's have a look at some problems. All right, so for this question right here, we're starting really straightforward. Y equals x. So we're going to complete the work here for reciprocating y equals x here. So here we're going to start with a table of values. And if you just plug in the values for y equals x, I mean, they're equivalent. The x and the y coordinates are the same. So this will be negative 5, negative 2 becomes negative 2, negative 1.5 becomes negative 1.5, and so on. Okay? Each one of those values maintains its identity through that function. Now, the reciprocal function is simply going to reciprocate that. So instead of negative 5, we'll get negative 1/5. Okay, instead of negative 2, we're going to get negative 1/2. instead of negative 1.5, which is the same as negative 3 over 2, we're going to get negative 2 over 3. Okay, negative 0.1, this is the same as negative 1/10. It's going to become negative 10. Now, 0 becomes undefined when you reciprocate that. 1, however, becomes 1. 2.5, now think about that, that's like 5 over 2, 5 halves, will be 2/5, and 4 will become 1/4. Okay? So now, what this looks like, the original, okay, essentially we just connect those points right there. Okay, it's going to be the line that looks like this. It's going to go through all of those little points right there. Now, what the reciprocal is going to look like is, first of all, this is going to be undefined. Now, we've already established that undefined is likely going to mean a vertical asymptote. So I'm going to put a dotted line there, and that's hard to see here. I'll try to make those big. But it's going to go through where x was equal to 0, because that's where I got my undefined. X equals 0, couldn't do anything with it. Now, I'm going to draw another little dotted line here, not quite so dark here, going across at 1 and negative 1. And where I intersect the original graph, those 2 points are going to be invariant. I'm going to make those nice and big so I recognize those. Those are invariant, meaning those 2 points are going to show up on the reciprocal as well. And I can see that one right here. The point 1, 1, 1, 1 is going to be on my reciprocal as well. Good. Now, at negative 5, okay, the y-coordinate became negative 1/5. So that's going to be like right close to there. Negative 2 became negative 1/2. Negative 1.5, okay, became negative 2/3. So that's going to be up in there. It's going to go through this point. The negative 0.1, which is way down here, is going to go way down here to negative 10. So you can see right now that this thing's actually going to swoop down like that. Now, the further to the left I go, just the closer it's going to get to the x-axis, but it'll never actually get there. Over here, 2.5 became 2/5, so it's going to be right there. 4 became 1/4, and actually the behavior is going to be the same as it was on the other side there. Okay, and there you go. So I've got this vertical asymptote at x equals 0. I've got this horizontal asymptote at y is equal to 0. My domain is that x can't equal 0. My range, okay, is that y cannot equal 0. Okay, you should see the link there. And again, just I'm going to keep saying this, that's not always true, but in this course that's a pretty safe bet there. All right, now the next thing we've got here is just a table where we can put a lot of that stuff in it. Okay, so my domain here, like we said, was x can't equal 0, the range, y can't equal 0. Oh, whoops, sorry, I'm getting ahead of myself. I'm sorry. For the original function, the domain was x is an element of the reals, and for the reciprocal, it was x can't equal 0. For the range, y was an element of the reals, and then for the reciprocal, y cannot equal 0. The x-intercept was going to be 0 for the original function, 0 for the y-intercept for the original function. Now, notice these are all grayed out here. It's because with the original function, because it's not a rational function, we don't really talk about verticals, actually asymptotes at all or invariant points. But here, for our reciprocal, we can. Now, our x-intercept, it doesn't actually hit the x-axis. For our y-intercept, again, doesn't hit the y-axis. Now, that's not necessarily true. If that's not going to be the same for every function, but it works for this one. Our vertical asymptote was that x was equal to 0. Our horizontal asymptote, y was equal to 0. Now, our invariant points, we saw one from the chart there at 1, 1, but there was another one here at negative 1, negative 1. That one didn't change as well. So negative 1, negative 1. Good. Okay, now let's take a look at this next one. If y equals x minus 2, we're going to identify the characteristics and sketch it here, okay? So if we plug that in, Essentially, we're just going to reciprocate that. My domain, when I take a look at that, is going to be x cannot equal 2, because that's going to make that function undefined there. My range. Well, I'm not 100% sure about my range until I graph it, okay? But if you think back to what happened in the quadratics chapter, when you had x minus 2 there, all that did was move the graph 2 to the right. If I take this graph and move the whole thing just 2 to the right, that's not going to change my domain, my range. My range is going to stay the same. So if it was y couldn't equal 0 in the original, it's still going to be y can't equal 0. It's not going to have any x-intercepts there, okay, because again, I can't equal the x-axis there. But I will have a y-intercept. Now, this is the graph, or the equation of my reciprocal. Just plug in 0 in for that. Okay, that's all you got to do to figure out the y-intercept. Plug 0 in for x. That's 1 over 0 minus 2, or negative 1/2. My vertical asymptote will be that x is equal to 2. My horizontal asymptote should be y is equal to 0. Invariant points. Okay, well, I'm not 100% sure of that. Okay, I don't know, but I can figure that out because this was my original function. I know that when this is equal to 1 or negative 1, I'm going to get invariant points. So I'm going to kind of cheat a little bit. Let's just go back to the original function because that's easier to work with. If I bring 2 over, I'm going to get x is equal to 3. So this would be 3 comma 1. That would be invariant. If I bring this 2 over, I'm going to get positive 1. So that'll be positive 1, negative 1. That would be invariant. So I already knew what the y coordinates were supposed to be. I just had to figure out what the x coordinates were. So let's plot those. So 3, 1, 1, negative 1. Those are my invariant points. I already knew that I would have the vertical asymptote through there at x equals 2. And so now, oh, and by the way, I knew that my y-intercept here was negative 1/2. So the graph must look something like this. Slide down, whoops, whatever. Slide down, goes through there, and then bends out like that. Okay. Whoops, sorry, you can't see that. That's what it's got to look like here. Now, notice it's basically the same graph, and that's because we are reciprocating a linear function. That's typically what it's going to look like when you reciprocate a linear function. Okay, so you can almost predict the behavior there. Okay, let's take a look. Let's take a look at another. So we're going to sketch the graph of the reciprocal on the same grid here. Now we're going to reciprocate this negative 1/2 x plus 2. Now when I do that, I already know that the x-intercept is going to become my vertical asymptote. So right there, I know that I'm going to lose positive 4. So my domain is going to be x cannot equal positive 4, and that's going to be my vertical asymptote. I know that this point, because its y-coordinate is 1, is going to be invariant, and this one, because its y-coordinate is negative 1, invariant. So 2, 1, and what's that? 6, negative 1. Going to be invariant. The original function goes through a y-intercept of 2. All I'm doing is reciprocating the y-coordinate, so that's going to become 1/2. Okay? And so now in almost every case here, when I've done this, the range, okay, has been that y cannot equal 0. That's because that has become our horizontal asymptote. Now that's not always going to be like that, but for right now that covers it. So this graph's going to look something like that. So my x-intercept, again, it doesn't have any because the asymptote is on the x-axis, but the y-intercept here was positive 1/2. You can see all those pieces there. Okay, let's try one more. Take a look at this one right here. Okay, again, I know that my x-intercept is going to become my vertical asymptote. Now, can't quite see that. Looks like, what is that, negative 2 and like 2/3. So like, what is that? X cannot equal negative 2 point, let's say 7. That's because my vertical asymptote is going to be at x equals negative 2.7. My range, well, this is a linear function here. I'm going to assume that y cannot equal 0 because the horizontal asymptote will be y is equal to 0. My invariant points are going to be where the y coordinate is 1 or negative 1. Now that looks to me to be like negative 3.3 comma 1. And I'm just guessing at that point. It's hard to read that off here. But this looks like negative 2 comma negative 1. That looks good. My y-intercept for the original was negative 4, so my reciprocal will be negative 1/4. Okay, all I'm doing is taking that value and reciprocating it. And my x-intercept, again, there won't be any x-intercepts. And because of where the invariant points are and that y-intercept, it looks to me like the graph's got to look something like this. And then like this. And there you go. So just to quickly sum up here, if you've got an original function that looks like this, if it's got a positive slope, then your asymptote's going to go there, and your graph's going to look something like this. Something like that. But it's got to go through where y is equal to 1, where y is equal to negative 1. On the other hand, let's say that your original function's got a negative slope, then again, there's your asymptote, okay, and it's going to look like this. Coming around, and then this is going to come up like that. It's basically, if you're reciprocating a linear, everybody, it's going to be one of those two graphs. Okay.